All right, I'd like to demonstrate how to measure a pair of Bluetooth hearables. And part of that is mounting them on hats with its anthropomorphic ears to get a more realistic representation of how a human would hear with these hearables in their ears. So for starters, I'm going to use the Portland tool and die Bluetooth interface to pair to the earphones. And then I'm going to use Audio Connect 2 to actually connect and power the TEDS microphones inside the ear simulators, as well as I used for my SEM microphone to calibrate the mouse simulator. After I measure frequency response, THD, and left-right balance, I'm then going to measure the send response of the hearables. And last but not least, I'm going to show the left-right difference. So let's get started. So I got to hit go, and it's going to tell me, do I want to pair my Bluetooth headphones? And I'm going to say yes. So I'm going to turn these into pairing mode. The white light should flash in a second here. And then the Portland tool and die is going to go look for any devices that are open for pairing. So we see we have the AirPod Pros here. So I just hit OK. And once connected, the light should turn green, which it does. So now it's paired. And then it's prompting me to put the earphones in the ear simulator. So I'll do that right now. We'll start with the right ear. And I'm not going to worry too much about the seal right now because it's a bit tricky. I'm going to use SoundCheck to do a seal check to make sure I have a snug fit and that I'm got decent bass output. And the way I do that is with the virtual instruments. So it asks me, do I want to check the headphone seal on the ear simulators? And I say yes. And it brings up the signal generator playing pink noise on both the left and right ear. And now we can see the real-time analyzer showing me essentially the frequency response of both left and right ear. So I have a good seal on my right, but not on my left. So I got to tweak that a little. So I just kind of make sure I get a snug fit here. I get a little brief overload, so it'll take a second to settle. But that's okay. SoundCheck will just ignore the overload. And once I get a good seal on my left ear, I can hit continue. So I think I have it pretty well sealed now. So I'm just going to hit enter, and we're going to measure at 96 dB SPL. So the next step is a step sign in 12th octave frequency resolution from 20 hertz to 20 kilohertz. And we will see the frequency response as well as what's called the diffuse field corrected response, which takes into account the ear simulators on hats. There we go. So now we see the frequency response, green and red, a left and right ear. We see the diffuse field corrected, which means ideally it should be more or less flat when we subtract out the ear simulator, which it looks pretty good. And then down below, we see the difference between the left and right ear, the tracking. For the most part, it should be 0, which it is. We've got a little bit of a notch down here, so there's a little difference. And then on the bottom graph, we have total harmonic distortion, left and right ear. So now it asks me if I want to measure the microphone response, otherwise known as the send response, and I say yes. And we'll hear pink noise played out of the mouth, and we will get the frequency response of the send up here. So essentially I'm done now, and it's done asking me whether I want to measure another pair of headphones, so I may want to clear the pairing, or I may want to do some more things with it, so I'll just say no. And I also have information about the sensitivity of my headphones, earphones, as well as the sensitivity of the send response. So now I'm going to demonstrate how to measure these ANC headphones, both with pink noise, kind of a stable background noise, as well as speech, a dynamic signal, which is going to be more difficult to attenuate real time. So in order to make this measurement, I've calibrated a source speaker with pink noise for starts. And I'm going to play it at a known sound pressure level, like 90 dB SPL. And then I'm going to measure the sound field, both with a reference microphone, which will be outside the ear cup, and the ear simulator inside the ear pinna. And that will allow me to look at the difference or the attenuation from the outside to the inside, which is how a normal human would hear. So let's get started. I'm going to play pink noise. I'm going to start the real-time analyzer. And we can see we have two curves. So the blue curve is actually the reference microphone, and the green curve is the ear simulator. And if I want to, I can actually correct for the ear simulator with what's called a DRP to ERP correction, and this should make them be almost about the same. So now that I've removed that, I should be able to see the live difference between the reference microphone and the ear simulator. So let's just put the headphones on without active noise cancellation turned on, just to look at the passive attenuation. Make sure I have a good seal. And we can see if now I have a difference of so many dB between these two curves. Now, if I want to, I can just show the calculation of the attenuation. And I've chosen to show it in a different graph to make it a little easier to see. So I'm going to drag it down here. And we can see we're getting about 30 dB of attenuation at the really high frequencies. I can maybe increase that. But I'm getting next to no attenuation at the low frequencies. So now if I turn on my active noise cancellation, I should see both the passive and the active noise attenuation. All right, so now let's turn the active noise cancellation on circuit. And I'm waiting for the light to flash blue. There we go. Now we should see, oh, here it comes. The low frequencies, the active noise canceller is kicking in. So that's great. We do notice though, it's not doing a great job around 1 kilohertz. And that's one of the challenges of designing noise canceling headphones, is there's kind of this crossover frequency between active at low frequencies and passive at high frequencies. So back to the drawing board, and maybe we can improve this, but I'm getting about 25 dB at the low frequencies and about 25 dB at the high frequencies, but only 10 dB around 1 kilohertz, which is actually where the ear is most sensitive. Okay, so I just showed you the attenuation with active and passive, this purple curve, which I've saved now. And now I want to try to use a dynamic signal like speech. So instead of playing pink noise, I'm going to come over to the signal generator and load a WAV file. So one of the signals I like to use is called ITU Real Speech. If we go to the SoundCheck 21 folder and look under WAV files, we'll see there's actually one called Real Speech. And again, I've calibrated the mouse simulator, or in this case, the source speaker, and for 90 dB SPL. So if we hit play,
the shelves were bare of both
we hear a real-time change in signal. And what I'm going to do now is start recording, and we'll look at the live attenuation. I may also want to just speed this up a little and use fast time waiting so we can see it dynamically. So let's hit start.
The shells were
and
bare
record.
of both jam or crackers. A joy to every child is the swan boat.
The stems of the tall glasses cracked and broke. The wall phone rang loud and often.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
So can you see the difference between the pink noise, the purple curve, and the red curve, which is actually the real-time attenuation? Most of the time they overlap, but sometimes, depending on what's going on, it takes a while for the noise canceller to react.
The wall phone rang loud and often.
The shelves were bare of both jam or crackers. A joy to every child is the swan boat.
Okay. So we can see that the real-time speech is a much harder signal to attenuate as opposed to a more steady state signal like pink noise. And if I was designing these headphones, I would want to take into account how I can make my circuit respond quickly.